It's a piece of cake to bake a pretty cake.
Welcome back to the Physics of Baking with Emily
and Sophia. Today we'll be baking cookies while also teaching you about the basics of thermodynamics with some other fun physics facts along the way.
Let's get started.
So let's make our way over to the kitchen.
First thing we're going to do is preheat the oven to 350 degrees. The oven is a good example of convection.
Hey you guys, it's Sophia from Ratch Academy, and today I'm going to be teaching you about convection. Convection is the transfer of heat through a fluid. In our oven example, the fluid that we're using is air. In this pot example, the fluid that the heat is transferred through is water. The water molecules closest to the heat source heat up first. This causes them to expand and rise to the surface. After they rise to the surface, they cool again and become more dense, sinking back to the bottom. This creates a circular motion. There are all kinds of real-life examples of convection, from the rise and fall of ocean currents to the convection of magma under the Earth's crust. The next step in our recipe is to melt the butter, and we're going to use the microwave to do this, and the microwave uses radiation to transfer heat. And radiation is the transfer of heat through electromagnetic waves. Hey, it's me again. I'm back to talk about radiation, another form of heat transfer. Radiation heat transfer is when thermal energy is exchanged through the laws of electromagnetics. The way microwaves use radiation for heat transfer is by flipping their electromagnetic fields. As the polar water molecules reorient themselves to match the electromagnetic fields, the friction that they creates heat energy. Another fun thing about microwaves is they actually use standing waves. The standing waves in a microwave actually leave little spots of unheated food. This is because the nodes of the standing waves have no movement, so the molecules in those areas won't reorient themselves or have any friction or heat transfer.
Even though we're not using the stovetop in this recipe, we're still going to talk about it because the stovetop is a good example of conduction. Conduction is the transfer of energy when two materials are touching.
Conduction is the last form of heat transfer that we're going to be talking about today. Basically, it's the flow of internal energy from a region of a higher temperature to one of a lower temperature. This is caused by the interaction of the particles with each other. As the molecules closest to the heat source heat up, they will start to vibrate and move faster. This will be passed on from molecule to molecule. The conductivities of materials varies from material to material. But generally, solids are the best at conducting heat. This is because molecules are more tightly packed together in solids than they are in gases or liquids.
Next, we're going to mix the butter and sugar until they're well combined. Physics fact! Rheology is a branch of physics that deals with the deformation and flow of matter. During mixing, dough is subjected to extreme deformations.
So, the less than rich yolks work as an emulsifier, helping the butter and sugar whip up especially light and fluffy.
Egg whites entrap more air while contributing more water, encouraging steam and gluten formation. I got it. Yay! Okay, good job everyone.
And mix it up.
Okay, look at that.
Don't
spill it, but look at it.
Next we're going to add our flour, baking soda, and salt. So this will really create the doughy texture that we're all familiar with when baking.
I'm going to add the flour.
And it's one... Yeah,
We're
that's
not-
physics.
That's rheology.
That's
Chemical. That is chemicals. Next thing we're going to do is add the chocolate chips. Fun fact, because of the fat content in chocolate, a whitish gray material forms on the outside of the chocolate. This is because the fat and the cocoa have different physical properties, and when they're exposed to warm temperatures, they separate. Now I'm going to add the chocolate chips. How fun.
With an increase in temperature, the eggs become more resistant to deformation, which changes the rheology of the dough.
That's one of the reasons why eggs are so necessary in cookies. They help with the structure. Now we're going to cool the cookie dough. Cut. During sheeting and molding, deformations of the dough are at an intermediate level. Gravity!
Ow!
I'm kind of scared of ovens, to be honest.
Hey guys, it's Emily from Ratch Academy. So I'm going to be talking a little bit about what exactly happens when you heat various foods up in the oven and why it is necessary to do that in the first place. So the basic principles of this concept can be explained using the Gibbs free energy equation, which is what I'm writing out right here. So in this equation, change in G equals Gibbs free energy. So what the change in G can tell us is whether a reaction will happen spontaneously or if it needs anything added for it to happen. When the delta G value is positive, that means that the reaction is non-thermodynamically favored and will not happen spontaneously. But if it is negative, that means that it is thermodynamically favored and will occur without anything added to it. One of the other variables in this equation is delta H, and this represents the change in enthalpy. Enthalpy is defined as the sum of the internal energy and the product of the pressure and volume of a system. So to explain this in a way that might be a little bit easier to understand is to compare enthalpy to heat energy. Enthalpy is like the potential energy of a system, whereas heat is the transfer energy, so it is a kinetic energy. In this example, the faucet and bucket both contain water at the beginning, similar to a system's constant state of enthalpy, without any outside influences. So when the faucet is turned on and water flows, this is comparable to heat transfer. The difference between the initial and final enthalpies are directly proportional to the heat transferred. So a negative Q value, which is heat energy, will give you the change in H value. So the change in H value can tell us a lot about a system. If the value is negative, then that reaction is exothermic, meaning that it releases energy when the reaction happens. If it is positive, that means that it is endothermic and takes in energy. The next variable in the equation I'm going to talk about is entropy. Entropy can be defined as the measure of unavailable energy in a system, but is also commonly thought of as the disorder of a system. The entropy of the universe is known to always be increasing, and this goes along with the second law of thermodynamics, which states that energy becomes more dispersed over time. This concept can be seen in our everyday life through things like campfires or just boiling water because there's gas being formed. These gas particles are more free to move around than the solid of the wood before or the liquid of the water before, which leads to an increase of disorder in the system. So now going back to the original equation, we know that the enthalpy value will be positive because it is endothermic, and the entropy value will be some constant. So the only thing that we can do to make this change in G value negative is to increase the temperature. And doing this will make the change in G negative and therefore spontaneous. So this kind of gives you a brief explanation on why most foods are dependent on an increase in temperature for them to either cook or bake.
We did it, you guys.
We did it.
Physics. All because of physics. We couldn't have done it without you, physics. Here are our cookies that we baked, and now we're going to taste test them. I'm so excited. They're getting cakey.
I'm sure you are all thinking right now, wow, those cookies sure look good, but I wonder how many calories are in them. This, when given the right information, is actually very simple to find. First, however, it is necessary to understand what calories are, and they're simply a unit of energy, and the way we find them is to look at the heat energy. Heat energy can be solved for using this equation, where Q equals the heat energy, M equals the mass, C equals the specific heat, and change in T equals change in temperature. Heat is measured in joules. And so to convert this to calories, we are given that 1 calorie equals 4.184 joules of heat. With the resources and information that we are given, it is a little bit challenging to solve for the heat energy, so we're just going to use the number 730 to do a little sample calculation. So you do stoichiometry and do 730 joules on top times 1 calorie over 4.184 joules because they are equal to each other, and then you get the outcome to be 175 calories.
Thank you for coming along on this physics journey with us. We hope you learned a lot.
Yay!
What was your favorite part?
Oh cool, my favorite part was eating the cookies.
My favorite part is when we learned about lecithin. As a parting message, we just want to say atoms are the building blocks of life. And atoms make up this cookie. And atoms follow the rules of physics.
And chemistry stole thermodynamics from physics. Thanks for watching.
Bye.
Are you still here, Lee?
Oh my gosh, are you still here?